Good afternoon, everyone. Welcome to the SLDS webinar. Today our speaker is Professor Jing Lei from Carnegie Mellon University. Jing is our chair-elect of SLDS in 2025. He is a professor of statistics and data science. He got his PhD in stats from Berkeley in 2010 and already a full professor since 2022. Jing's research focuses on providing rigorous insights into popular algorithms in practical context. He has done pioneering and foundational work on predictive inference, including conformal prediction and cross-validation. He developed advanced theory and methods for high-dimensional matrix data, including sparse PCA and network data, with successful application in single-cell multi-omics data analysis. He's also among the first researchers to study differential privacy in a statistical context. Jing is a fellow of IMS and ASA. He also serves as associate editor for many top journals, including Annals, JASA, JRSSB, and served before as AE for Sinica and the Journal of Korean Statistical Society. Jing has received multiple rewards, including NSF CAREER Award and Gottfried Noether Young Researcher Award in 2016. And in 2022, he's a recipient of the Leo Breiman Junior Award. And in 2024, he was awarded the IMS Medallion Lectureship. So without any further ado, let's welcome Jing.
All right, thank you. Thank you, Zhihua, for organizing this webinar series. This is really amazing activity from SLDS, and thank you so much. And also I thank everybody for participating in this SLDS online activity. So today I will share some of my recent thoughts and the progress in actually a little bit of everything. So this research problem originated from my investigation about conformal prediction a few years ago, and then I wanted to use conformal prediction to do like more rigorous and versatile model selection, and which led me to think about cross-validation. And then in this hybrid of model selection, uncertainty, and cross-validation, in this talk you will also see a little bit of differential privacy. So this is really like in the intersection of quite a few of my long-time research interests. And in the beginning, this is the slide showing the picture of two of my collaborators on this project. On the left is Tianyu Zhang. He is currently a postdoc at CMU and will be on the job market in this coming fall. And Hao Li is a third-year PhD student in our program. So I would like to motivate the problem and also provide some context through a real teaching story. In this past spring semester, I taught a class called Methods in Statistical Learning, which is cross-listed for senior undergrad and master's students. So in the first half semester, we covered basic classification and model building methods. So we start from simple things like logistic regression, and then we introduce the penalty, and then SVM, mixture models, and in the end, we went all the way down to neural nets, like random forest and neural nets. And in the second half, the students were assigned a data set for binary classification, and which will be their prediction computation. So this is how the prediction computation was run. I generated a training data set from Kaggle. So it's a popular open source website for people to share machine learning data sets. So it's not a big one. It's just it's a moderate one with about 5,000 training sample points and with 16-dimensional covariate. And I also provided the covariates in a test data set with about 1,200 sample points. And the students were asked to submit their predictions of the binary response in the test data set. Okay, so it's fairly simple and straightforward. So you have the training data with paired X and Y, and you're asked to predict the Y in the test. Okay, so in the end, so I received about 40, to be precise, it's 39 submissions. So some students, they teamed up. So then for each of them, I can just calculate the empirical test sample error rate, right? Just the test sample average of what proportion your prediction is wrong. Okay, and we see among 39 submissions, some of them have had a error rate as low as about like only 7%, and some of them can go way above 10% all the way to like 25%. So I believe this curve reflects, right, the general picture we have. Like most of the students, they know what they're doing, and they get the main ideas, and while some of them like basically fumbled the project. So, but my question is, who do I claim to be the winner? Well, the simple answer is, well, there are 3 teams tied to have the smallest empirical risk. But then I started looking at the next 3. They made maybe 3 more mistakes on the test set out of 1,000, like out of 1,200. Is it fair to really say that their prediction is worse or not as good as the 3 leading teams? So if we just take a closer look at it, right? The 3 teams achieved the smallest 82 out of 12,036, but there were 8 more teams with the empirical risk. Well, 8 more teams made like 5 more mistakes or less. So the question is, how confident are we in claiming that the first 3 models are indeed more accurate than others? So I'm asking this because they are empirical mean, right? And the test sample has its own uncertainty. How do we take into account this uncertainty in the test data? And in other words, what I really want is the confidence set of the winner. Okay, so the rest of my talk will be how I draw this vertical solid line. So essentially, to the left is my confidence set of the true winner. It's kind of big because it's understandable, because we only have 1,236 test sample point, and their performance are so close to each other. So it's really like, if you want 95%, and you have to go this far. Just to provide you a benchmark, the dashed line is the cutoff provided by using Bonferroni. Say I just do all the pairwise t-test and then correct for multiple comparison, right, using Bonferroni, and that method will be even more conservative. Okay, so we'll see how I draw that line, which gives us only 25 teams instead of 33 teams. And in the end, I will also show the output of other competing methods. All right, so let's look at an abstract version of this problem. So we have IID sample of a p-dimensional random vector. For simplicity, I will assume that the random vector has each entry bounded uniformly, almost surely. And the mu is the p-dimensional mean vector, and we are interested in finding the index from 1 to p, the index such that the corresponding entry in that mean of that mean vector minimizes. So it's the argmin of the mean vector. Okay, so the type of uncertainty quantification guarantee we look for is, suppose I output a theta hat from my data, right, as a subset of P, and I want the probability of each true Argmin index being included to be lower bounded by like a user specified level, such as 95%. Okay, this is essentially a discrete version of the M estimator, except that we're just trying to optimize over a discrete domain. And we allow for ties. So this is actually an important feature in our setting. So we allow for more than one elements in the Argmin. So it's possible that two coordinates, they are equally good. So they can both be the minimizer. What about the FDR for choosing boundary? So that is about how do we specify the coverage guarantee? I think so. Our procedure outputs p-values. So I guess if you get the p-values, then you can use the p-values to construct the corresponding FDR-based processes. Okay, so but in short, like I never thought about FDR for this context, not yet. But I think that's maybe a worthwhile direction to think about. Thanks for the question. So so how do we connect the abstract framework to the question we just asked from the prediction competition? So each R represents a fitted prediction model, and each I represents a test sample point, and the mu R is the actual risk of the R's prediction model, and XIR, so that's the R's entry of the I sample is the actual realized loss. It's the 0-1 loss in our classification problem. It's the realized loss of the R's prediction model on the I's test sample point. So, so actually, there are other, at least theoretically relevant scenarios. So we can think about election, where each R represents a candidate and each I represents a voter, and the mu R is the actual support rate for that candidate, and XI is the ballot reading for the I's voter. And here the randomness includes typo damage, machine error, or missingness. For example, the voter I may has like a non-zero chance to fail to submit the vote for any reason. Okay, so but well, we'll just focus the rest of the talk on the abstract format, and we'll come back to the prediction competition example later. Oh, Richard asks, what about asking for theta to be a subset of theta hat with probability? So that is another kind of, so it's a stronger way of coverage guarantee, and it has been considered in other papers on this topic, and we haven't done that yet. So like for now, we're just only considering the marginal coverage, but that like the subset kind of requirement has been considered by other authors. And as you can see, it has to be more conservative. Well, as I said, there are many other existing works. Actually, this topic has a long history. They dates back at least to almost 50 years ago. There are like a couple of books on selecting the best populations, right? And then 30 years ago, in this paper by Fuschik and Flach, it's based on an independence assumption among the coordinates, and where they can do some explicit calculations of the pairwise comparisons. And more recently, Hansen et al. In this paper, I think it's in the economics literature, they first considered the problem of model confidence set, and they developed a backward elimination method based on some parametric model assumptions. And more recently, there are like better probability tools available. For example, in this paper by Mogstad et al., they use bootstrap confidence set to infer about the ranks. And inferring a confidence set of ranks can be viewed as the dual problem of the confidence set of the winner. And so they construct a simultaneous confidence set for all these pairwise comparison. And also quite recently, a group of people in North Carolina State, they considered this problem using the machinery of E-value and sub-martingales. All right, so I will not go too much detail in this existing work, but I want to also mention that this problem is also related to the discrete M estimation, as I mentioned earlier, where you can just consider our familiar M estimation problem, but where you optimize over a finite and a discrete set. And this problem has an even longer history. And if you read the recent review paper in Statistical Science by Choirat and Seri, and you would know that the results on confidence set of the minimizer is rather scarce. And this problem also related to rank verification, with quite a few authors considering them, and also post-selection inference. And I will get back to the post-selection inference nature of the problem in just 1 minute. All right, so some notable features in this work. So as I said, there are many related work and also a long history. So here we allow P to be large. In the end, the P can be exponential to the to some small polynomial of n, and the components of each sample point can be dependent, and we don't know how they are dependent, right? And we also we have some mild conditions on the covariance matrix, the smallest and the largest eigenvalues, and we put no assumptions on the mean vector mu, which mean the next line, there may be arbitrary many ties or near ties at the minimum value or elsewhere. Okay, so this one is usually not allowed by many of the existing methods. Okay, so now I will just describe how we are going to construct our confidence set. So first, I will just relate it or reduce it to an adaptive mean testing or mean comparison problem. So because we require marginal coverage, right? So we only care about, for each individual R, actually being the argmin to be included in our confidence set with a prescribed confidence level. So it reduces to testing whether that R is in our argmin set, or equivalently, the mu of R is no larger than any other coordinate, or equivalently, mu R is less than or equal to the smallest coordinate outside of R. So that's the notation SR. Okay, so the two sample comparison we know how to do, but finding SR is hard because we don't know where SR is at for any given R. So if SR is known, then we just apply to a two sample t-test, we're done. But SR is known if we just estimate it from the data and plug it in, and say, for example, we just estimate this SR hat to be the argmin of the empirical means, then our test will suffer from what we call the selection bias, or double dipping of the data, because we use the same data to select this index, and then we use the same data to test a hypothesis based on that selected index. So this is a very well-known selective bias issue in multiple comparison. So how do we fix this? So because I said, okay, I came to this problem from cross-validation. So my first idea is, okay, we can use cross-validation to avoid the double dipping issue. So here's what I do. Instead of getting that S hat R from my entire data set, I get it from the leave one out mean. So this SR hat minus I is the argmin of my leave one out sample average. Okay, so now we know perfectly because we assume our data is IID, so that this leave one out argument is independent with the ice data sample. So how about we just evaluate that SR hat minus I on XI, and I compare it with my R coordinate on the ice sample, and then I take average over all sample points. Does this give me something closer to like asymptotically normal? Let's look at the simulation. And here, okay, so these are the histograms of the repeatedly generated test statistic. And the solid black curve is the standard normal that we want to. And the simple method is a double dipping one. And the split, the light green or teal histogram is the one that based on leave one out argument. So we can see that it's pretty much as biased as the double dipping method. So using leave one out cross validation to get the argument does not really solve the problem. At least it doesn't give us the expected asymptotic normality. So what's the problem? So the problem, the reason for asymptotic normality to break for such cross-validated statistic actually has its root in a more general theoretical story. So we know actually central limit theorem for cross-validation type statistics is non-trivial because we don't really have independence. So every term here, they are dependent with everybody else, because for the ith one, you still have this SI R hat minus I, which depends on everything else, right? So you don't have IID. And the recent insights from some theoretical papers about the asymptotic normality of cross-validation, so they require a notion of perturb one stability of the cross-validated loss. So that means that for each summand in that average, they need to be stable when we perturb one entry in the data. And actually in our case, so the focus is about this quantity x sub I evaluated at the coordinate SR hat minus I. And because this is where the global dependence comes from. Okay, so why this is not stable? Because if we change a single entry in some other sample point, that may result in an entirely different value for the Argmin index, the leave one out Argmin index. Once that index shift, it's a constant order of change when we evaluate it, when we evaluate that random index at the ith sample point. And unfortunately, that change of this leave one out Argmin index happens with probability a little bit too high, right? You can argue, well, if that doesn't happen too often, I'm still fine. But unfortunately, the probability of that happening exactly breaks the requirement. So, and also as validated from our simulation, the leave one out cross validation is not stable enough to provide asymptotic normality. And Tianxi asked a question on the chat saying, if you just use sample splitting once, so sample splitting once, yes, but that gives you a reduced sample size. So empirically, it works not as powerful as the method that we're going to see. And also, the inference about sample splitting once is conditional on like one half of our data or one part of our data that you use to find the index. Okay, so more about stability. Actually, Professor Bing Yu in Berkeley has been like thinking and advocating for stability for many years, and like in their what the PCS framework of data science. Stability is one of the 3 pillars for modern data science. Actually, they argue stability is necessary for data analysis. Actually, in our theoretical perspective, stability also facilitates, helps us to prove asymptotic results. Okay, so how do we stabilize the leave one out statistic? So once I realized the problem is lack of stability from the argmin or the mean, the leave one out mean, then I immediately thought about this is actually very similar to the sensitivity notion in differential privacy, right? So the perturber one stability similar to sensitivity, and in differential privacy, we know perfectly how to stabilize the minimum value from a vector, which is called the exponential mechanism. So in our case, you really just, instead of taking the leave one out minimum, you randomize it. So now I let the randomized leave one out minimum to be tilde S sub r, and which has weight proportional to the exponent to a negative number multiplied to the leave one out sample mean. Okay, so here the lambda n is a tuning parameter. I will get back to it later. So as you can see, if lambda n is positive, so that if the leave one out sample mean has a smaller value, that coordinate S will have a larger weight. So you're more likely to get that coordinate, but overall the process has to be randomized to have stability. And so in our application, we further average over this sampling randomness so that I take my xi s tilde r minus I. Not so I don't first randomly generate an index and evaluate it. I just take expectation over that randomness of the index sampling. So it becomes a weighted average of the coordinates in my ice sample. So I call that QIR. So intuitively, this quantity QIR is a stabilized proxy to the evaluation of the best competitor to compare with my R's coordinate to evaluate it on the ice sample. Okay, now with this randomized or exponential mechanism stabilization of my leave one out mean, I can propose a new test statistic. So it's the sample average of the difference between my R's coordinate, which I just hold out, and then QIR, as I said, is its best stabilized best competitor. And this is a picture showing you how do we construct that single summand in our test statistic. So I first take out the ith column because that's where we're going to evaluate. And then I use, the ith row. And I use all the other rows to consider the leave one, to compute the leave one out mean values. And I use these leave one out mean values to compute the weights. And then I use weighted sample outside of the R's column on the ith row. And then I sum them up, and then I take the difference. All right. So here are some quick remarks about this test statistic. So if you consider the conditional mean of the summand xir minus qir, under the null hypothesis that R is indeed in the argmin, then the conditional mean of this summand, given all the other sample points, is non-positive. Right? And the proof is just one line. right? Because you given all the other, basically you're given the weights. When you given the weight, and then you take the average over just the ice sample, then it becomes a weighted average of the difference in the mean values, because the weights, they sum up to 1, right? So if mu r is no bigger than all the other mu s's, this quantity has to be less than or equal to 0. And the tuning parameter lambda, it represents the balance between the power we want to have and also the stability we want to have, so that we can do valid inference. So the smaller lambda is better stability in the extreme case, lambda equals 0. Your Q is not really picking the better coordinates, but it's just doing a uniform average over all the other coordinates. And if you send lambda n to be very large in the limit, when lambda n equals infinity, your QIR is really just getting back to the leave one out minimum, the empirical minimum, which we know wouldn't be stable enough to have asymptotic normality. And all these methods and theory we're going to see later, they can be extended to cover V-fold version. So here I described the method using the leave one out cross-validation approach, but here you can actually do any V-fold, even for divergent V, because like V equals N is leave one out. And here I can present the CRT result for our test statistic. So as I said, if I just have some mild assumptions that my covariance matrix of the noise has eigenvalues bounded from above and away from 0 by constants, then after this conditional centering, my test statistic has asymptotic normality, where the asymptotic variance equals to the marginal variance of each individual summand, the comparison term. Although they are not independent with each other, but we can show that with the correct choice of lambda n. So lambda n has to diverge to have power, but it cannot be too big. So this small o square root n is required to accommodate the worst case. So in practice, it can, or in special cases, it can be much larger. We have further details in the paper. So here, this is not a very standard COT result you're going to see in the textbook, because our centering, DIR, that which is the conditional mean of XIR minus QIR given the leave one out sample. So it's a random centering, but we know that the random centering has a known sign on the right side, on the correct side, under the null hypothesis. We know that DIR is non-positive. Okay, so the proof idea has to do with some general argument about like weakly dependent data, and when you add them up, like, so this weak dependence is not like a martingales or mixing, because if you pick two arbitrary summand, it doesn't matter how far they are, like the I and J, but they are equally correlated with each other. So the correlation doesn't change when your sample point move apart from each other. So this is different from spatial statistics or time series. And so the problematic term is really that Q part, which involves the weight, and that weight depends on everything else, right? So what we do is, let's see like how each sample point contributes to the variability of weight. So to this end, let's consider the perturb1 dataset, where we perturb the J's entry by an IID copy of it. And we introduce the nabla J, which is this perturb1 difference. That is the difference between QIR evaluated from the original dataset and the QIR evaluated on the perturb1 dataset. And also correspondingly, the difference of difference, the perturb2, or which involves the perturb2 data set. So it's a nabla K and a nabla J. So you can view the nabla J as the first order stability and the nabla K, nabla J as the second order stability. And the key facts, so with our construction and the choice of lambda, and the QIR is stable enough such that the first order stability bound is smaller than 1 over square root n, the second order is smaller than 1 over n. And with these stability result, then we can use the corresponding martingale decomposition developed in this paper by Austin and Zhou, who first used these kind of techniques to prove CLT for cross-validation. So now let's look back to the previous histogram plot. We know that the double dipping, the blue histogram, is not asymptotic normal, and we also know that if we only use leave one out splitting, it's also not asymptotic normal. Now you may wonder, I have this exponential mechanism to stabilize it. Maybe that will do the trick. It's not the sample splitting's effect. So can I just use exponential weighting without sample splitting? And the answer is actually no. So here what you're seeing, the blue histogram is the weighting only without sample splitting, without the leave one out split. And the green one is the cross-validation only without weighting. And the red one is weighted plus cross-validation. So you do need both for this to work. So that means any CV or exponential mechanism alone is not sufficient to achieve asymptotic normality of our test statistic. So it's not the artifact of our proof. So like at least the numerical example shows that you do need both. So asymptotic variance is relatively more straightforward. We can just evaluate them, like just work as if they are IID. We just compute the empirical variance of these terms. Then the resulting variance estimation is consistent. So the idea is like just to give you some intuition, you use the total variance decomposition, and the conditional variance of this XIR minus QIR given each sample point. So that is the variance contributed from the weights, because I'm conditioning on my evaluating point. So the only variability is the weight. And we know that the weight is stable. So that part vanishes. And the second part is the variance of the conditional expectation on Xi. So that is the contribution of Xi in this variance. So, and if you imagine that the weights are so stable so that they're all the same, then this is really what we're doing in our empirical variance estimation. Okay, now we have a construction of our confidence set. So recall that we have this sample average of XIR minus QIR. QIR is the weighted average of all the other coordinates, right? And a level alpha confidence of the argument is it consists of all the coordinates whose TR after scaling, right, does not exceed the upper alpha quantile of standard normal. Okay, and this is valid because we know the sign of the centering, right, under the null. So that's the crucial part to establish the validity. So under the same conditions, we can show that this confidence set satisfies asymptotically the marginal coverage. Okay, so yeah, just a few remarks. As I mentioned, why this method works well, because we use the weighted soft mean. It eliminates the obviously bad candidates. So this is like selective inference, but without having to pay the price, like the high price I have to adjust for the selection, because I realized my selection using weights, and as long as the weights are stable, then I'm okay, right? And the results can be extended to cover unbounded noise distributions, and also the asymptotic results can be stated in a non-asymptotic fashion, so that we can allow for P and of course the covariance to change with N, so that for any specific P and N, as long as you and also you have the corresponding bound on sigma, then you can write the little o1 term by specific quantities involving, for example, log P, log N, and the eigenvalues of sigma. Okay, so you may wonder, okay, because I'm using the weighted average, so how powerful is this procedure? Let's look at the power of the procedure. What can we say about it? So for simplicity, I'm assuming that the minimum value of the true mean vector is just 0. Okay, because I don't think there's much loss of generality. You can always shift everything by the same constant to make the minimum value to be 0. And now, like for notation, I don't want to squeeze in too many letters and symbols, so that the L infinity norm upper bound is just 1 for all coordinates. And so here, the beta n is roughly speaking the scale at which like the cutoff for the coordinates to receive substantial weights, where here capital V is the number of cross-validation folds, and in our leave one out version, V is just n. Okay, and now I define this confusion set. So for each R, because I want to tell whether R is in my Argmin set, so I define the confusion set related to R is the coordinates S such that whose mu S value is larger than half of mu R, but smaller than or equal to that beta divided by lambda. So why I call this set confusion set? So the first requirement of S in the set is bigger than mu R over 2. So that means like mu S is close to mu R. Right, so like for mu S smaller than beta n over lambda, and that means this index will receive some non-trivial weight. So if we have many coordinates of this kind, like they're not too much worse or sometimes even better than mu R, and like, okay, they're not too much worse or too much better than R, but they receive a lot of weight. So that means in the weighted average, it's less likely to separate R from the weighted average, because when mu R is positive, we want to reject R, right? So once our test statistic is unable to separate them, then it has less power. So this is intuitively why this confusion set, its cardinality somehow reflects whether this procedure will have high power against this coordinate R. And our formal theorem says, under our assumptions, if the confusion set is non-empty, right, then the confidence set will exclude this coordinate R with nearly full power, asymptotic full power, if mu R is greater than or equal to, of course, we need to have this reciprocal of lambda, because everything is multiplied by lambda in that weight. And the lambda is just slightly smaller than 1 over square root n. And here, the dependence on P and N are log-log. So they're actually much better than log P or log N. And the real deal comes in the cardinality of the confusion set. So, but in the extreme case, right, if you're unlucky, everything can be in the confusion set, then that part is log p. But if you do have like many like very bad coordinates, and those coordinates, and those coordinates will not affect your power, and only the coordinates in the confusion set will. And in the special case, when the confusion set is empty, so that means our algorithm will not get confused. So it actually achieves the parametric rate, or the parametric asymptotic power guarantee, so that as long as the square root n times the mu r goes to infinity, and we have asymptotically full power. Okay, so overall, the smaller confusion set is, the better power we have, and there's just a global upper bound on the confusion set, which is just all the non-zero entries or the positive entries, but smaller than or equal to that beta n divided by lambda n. So, but this beta n divided by lambda n is has larger order as log p divided by square root n. And I will talk about possible improvements. So that's the idea of the proof. As I said, there are 3 tiers: the near optimal tier, and the confusion set, and the irrelevant set. I will just skip the details. And here comes actually a crucial part of our algorithm. How do we pick the lambda n, right? So essentially, our algorithm requires only one tuning parameter, which is this lambda n multiplier. And we know that, well, in the worst case, you will need lambda n to be small o square root n, but in most cases, it can be bigger. And the bigger we have, the better power we will have. So now, suppose we have a set capital lambda of candidate values. So what we're going to do, we're going to pick the largest one that has the good stability, right? So, and how do we empirically verify the stability? So on the left hand, we're going to evaluate, right, the nabla j, the leave one out version of our Q value, which is the weighted average from leave one out cross validation. So we want the variance of that quantity to be, as our theorem required, right? We want it to be of small o 1 over square root n, so that the variance is of small o 1 over n, and we want to calibrate it with the asymptotic variance itself. So that's the standardization part, the variance of our xir minus qir, and the epsilon is our practical reflection of that small o term. So how small it should be, and so for example, we realized that epsilon can be 0.05 or 0.08. It's not really sensitive. Like I believe currently we use somewhere between 0.05 and 0.08 for leave one out. And if you have twofold, well, you need to find the corresponding epsilon if you change your number of folds. And so the problem is, how do we estimate these two quantities? Right? Once we estimate these two quantities, then we have a practical procedure to choose lambda. So remember that the variance of xir minus qir, we have already done it in our asymptotic variance estimation. So that's required to construct the confidence set, and where we just use the empirical variance of the xir minus qir. And so we only need to estimate the variance of the stability term, the perturb one difference of qir. And just to help you remember, nabla j qir is a weighted average of xis for s not equal to r, and but we take the difference between two weights. One is the leave one out weight, the leave I out weights. One is the leave I out, but with j's entry perturbed weights. Okay, So what we do is we construct a triplet of indices I, j, j prime, and each time I do leave two out weight estimation, and for one of them I perturb one of the entries, and that will mimic the behavior of the leave one out. So then I just repeat this sampling of these triplets many times. So I basically use J and J prime as this perturb one to mimic the perturb one estimation of the weights, and then I evaluate everything on the I. Okay, so I randomly sample many such triplets, and then I evaluate the corresponding proxy to nabla J QIR, and I square them. I take the empirical variance. Okay, so that's the estimation. Is fairly intuitive and easy to implement. Okay, so now I'm going to show some numerical experiment to compare with existing methods. So let's first see their performance in some simple scenarios. So I consider my mu as a base vector multiplied by a positive number to determine the separation between the different coordinates. So the base vector is 100 dimension. It has two shapes. The first shape is what I call linear increase. So it increases from 0.01 with equal increment all the way through to 1. And the other base vector has the shape of 3-tier. So the first coordinates are 5 coordinates are all 1. So we have multiple ties at the winner. And the next 5 coordinates are 1.02. So they're actually very close to the minimum, but there are also many of them. And the rest, 90 of them are 10. So it's very bad, should be irrelevant. But the problem is, the challenge is, how do we separate the second tier 5 coordinates and f from 1 through 10? So when f equals 0, sorry, f is from 0 to 10. If f equals 0, the mu vector is flat. This is actually arguably the least favorable or the most challenging case to guarantee type 1 control. And when f is large, so your signal to noise ratio is much higher. And we also set the covariance to be topless and with varying strengths of correlation. And we compare with Bonferroni, which is just a pairwise comparison with Bonferroni correction. And this Fuchs-Schick and the Flock method, assuming which relies on the noises being independent across coordinates. So it's valid when rho equals 0, but not, like, theoretically not so much for larger value of rho, but empirically they actually perform okay. And the rank inference method from the Smokestad et al. Paper using simultaneous confidence set of pairwise comparison. And so what do we show you? Because we have so many settings and so many methods, and each type of this base mu vector has 55 parameter settings. So it's 11 values of the constant multiplier, the separation factor, and the 5 values of the strength of correlation. So for each of these combination, we repeat 100 data sets, and n equals 1,000. And we calculate the average coverage frequency for all R for each parameter setting. So on the next slide, you see, so you should see, so for each method, there are 55 frequencies of coverage. So in the increasing landscape, we see Bonferroni is very conservative, and the other method, the FP and our leave one out and the rank inference, they have some like 5 dots exactly close to the nominal level 95%, and the other values being more conservative. This is reflecting, because if you want your method to be valid, it has to be valid in the least favorable setting, which is the flat signal. So when you have the flat mu, and they provide a reasonably good coverage near the nominal level for the flat mu, but they are inevitably like more conservative for other kind of mu's. And our method is relatively less conservative. And you can see for the 3 tiers landscape and our method again. So like they're all valid, meaning that the coverage frequency is 95% or higher, but our method is the least conservative. So now let's count the number of false negatives, which is the power. So for each setting, we compute the average number of false negatives. So that means the number of suboptimal coordinates incorrectly included in the confidence set for each method. So because we have 4 methods in comparison, so we just subtract the other method from the number of our method. So a negative value means that our method is more powerful. So the top row is the linear mu base vector, and the bottom row is the 3 tiers base vector. And in most settings, right, among these 6 times 55, among most settings, our method is at least as powerful as others, except for this nearly flat and nearly independent setting when compared to the Fuchs-Schick and the Flock method, which is specifically tailored to independent IID noise. Right, and I also would like to show you a more like realistic or interesting example, which is the tuning of lasso. So we have 300 dimension linear regression data, and the beta is sparse. So we have a training data sample size of 160, and the test sample size, a small one and a larger one, so 40 and 60. So our beta sub eta is the lasso penalty because lambda has been used. So I use eta to denote my lasso penalty. And basically I have 100 eta values that's given by the GLM net package, and I want to pick which beta hat eta is the best linear regression coefficient, and I want to get this from my test sample. Okay, here my mu-r is the conditional regression risk given that R's estimated value of beta hat. So in this example, we're really using our method for tuning parameter selection, and we hope to construct the confidence set of the best tuning parameter. So what you see is the percentage of exclusion. So, and we know that the best coordinate is about 39. And we're comparing Bonferroni, which is red, so the power is very poor. And there's leave one out, which is our method given by the green line. And this rank inference method, it's among all the competing methods, this one is the most competitive. And it's plotted as the blue curve. So with small sample size, from small sample size to larger sample size, the power goes up, and our method offers the best power while maintaining validity, because at the smallest, at the single best model, the coverage probability is 95% or higher. And this is the bottom left plot is showing you the quality of normal approximation. As you can see, when the sample size goes up, like at least at the right tail, it's closer to normal. And also, I have to mention that this setting, right, we are not really in the boundary of the null hypothesis. because the boundary of null hypothesis where that centering is exactly 0, that requires the mu to be flat. When the mu is not flat, right, the centering is not 0, so the actual comparison to normal will be a little bit off. And we have more details about that part in the paper. And the plot D is showing how high the correlation is. So indeed, our method remains quite competitive even when the correlation is super high. Actually, there is argument saying that high correlation actually favors the ranking inference method. Well, let's we are 2 minutes over the time, so I will just spend 2 more minutes to show you the data application results. So again, we are back to the prediction competition. We actually have 2 years of data. So in the first year, 2023, the N is very small, only 183. We have 44 teams, and in 2024 we have a much bigger sample size, and the P is 39. Okay, so in 2023, we are able to exclude 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We are able to exclude 12 from 24, and which at least doubles like the power of any other competing methods. So the solid dots are the ones excluded from the confidence set. And again, 2024. So because of the increased sample size, the rank inference method becomes more powerful, but our method remains the most powerful. That's it. And there are further thoughts. I think this is really the beginning of a thread of research. So the alternative is a composite, sorry, the null is a composite null. And our method will be conservative if we're not on the very corner or boundary of the null hypothesis. So we may want to focus on confidence set or intervals of the gap of the mu value. So it's the difference between the current one and the best one outside of R. And we can consider integrate the CV with cross-validated model selection. So who will give us the candidate models? What if we use cross-validation to give us the candidate models in the first place? And how do we integrate our method? And in that case, we'll have multiple versions of mu-R, because each photo of CV will give us a slightly different estimate, and which will produce some variability in R. And we can also think about how do we find the confidence set of not just top 1, maybe the top K. And in general, I think we need to spend more time thinking about stability. How do we stabilize the Argmin? And there are other approaches. And how do we quantify the stability of the stabilized Argmin? And also moving away from IID, like how do we treat this online learning scenario just to refine or update the confidence set when we have streaming data in a changing environment? And I think this has a connection to things like multi-armed bandit. Okay, sorry for going over time, and thank you for your attention. So that's the link to the paper, and this research is partially supported by NSF and NIH grants. Thank you.